Could $27 million be saved? That's the question we are going to ask and answer today in this video. Because last month, Penpie Finance on September 2024 got hacked and $27 million got stolen. On the screen right now, you can see the tweet with all the traces of the attack and how the money was drained from the smart contracts. You can also see here on-chain message of the Penpie, whatever you name this protocol, finance team, reaching out to the attacker address, sending a message on-chain on, I think it's Optimism or Ethereum, I'm not sure where it got hacked. We acknowledge your exploit of our protocol. We are open to negotiating a bounty in exchange for a safe return of the funds. Please contact us to discuss terms confidentially. No legal action will be pursued if the funds are returned. Let's find mutually beneficial solution. And here they left some details to reach out. This was a catastrophe. I think until this day, the money was not returned. And in this video, we're going to talk about Penpie Finance, what it is, the fact that it's been through audits, the cause of the attack, and the most important thing, asking the question if we could prevent this attack. We're gonna discuss a concept called mutation testing and how it could help detecting and preventing the attack and preventing this loss of $27 million. And also we'll see a super cool tool that will help us to integrate mutation testing into our smart contracts and Solidity code in order to detect and prevent these attacks before it becomes catastrophe. So without further ado, let's get started. Let's start with some intro about this attack. So almost $30 million, 27.3.4 were stolen from Penpie Finance on September 2024. This protocol Penpie is integrated with Pendle, which is a very, very big protocol on Arbitrum. So Pendle allows you to maximize your yield and trade yield tokens, which is something pretty innovative for DeFi. It's out of the scope of this video. We're not going to cover what Pendle is and how it works, but what you have to understand in order to understand this attack is that Penpie is a protocol that integrates with Pendle in order to boost the yield that you're getting from Pendle. And this Penpie protocol is part of Magpie DAO. And the interesting thing is that the Penpie protocol got audited 2 times by very non-audit teams, very famous and strong audit teams, I would also say. Zokyo audit report and Watchpug's audit report, 2 very strong high-end audit teams reviewed the smart contracts of Penpie and they couldn't spot the vulnerability. Now, before we cover the root cause of this vulnerability and we see how we might have detected it with something called mutation testing, I want to take a look at these audit teams, Zokyo and Watchpug, to show you that it's not just another team, not just another auditor. It's strong teams with big clients, with a lot of reputation. Let's start with Zokyo audit firm. You can see here that they audited a lot of protocols and chains, 1inch, you're probably familiar with it, Aurora, Chainport, a lot of different networks and chain were audited by Zokyo. The second audit was audited by Watchpug, which is another audit group. As you can see here, they are the second place in all-time leaderboard in Code Arena, earned more than 800k USD in rewards. So you can say they are a legit team. Also in Sherlock, they earned more than 250k USDC. So it's not just another audit team. It's like 2 very strong audit teams audited the protocol and couldn't find this exploit and vulnerability. Now you might think, all right, if these 2 audit teams couldn't find the vulnerability and the cause, maybe it's very complex vulnerability, right? But you will be surprised that the actual root cause is reentrancy attack, and you're probably familiar with reentrancy attacks, not something super new. We know we are familiar with reentrancy attacks, and now you might ask, no way. It's 2024, September 2024, and $27 million plus are being stolen from a protocol using a reentrancy attack vector. How come? How did they miss it? And the answer is the developers of the Penpie protocol did not follow the checks effects interactions pattern, and the vulnerability of the reentrancy existed within an owner-only, admin-protected, out-of-scope function. So you're probably familiar with all these invalid issues that you submit to audit competitions because it's out of scope, out of scope. This function is controlled by only the owner. It's not user-facing function. It has access control. So we don't care that we don't follow the checks, effects, interactions pattern. That's exactly the case. That's what happened here. And we can read here from the post-mortem article that Penpie published. By the way, you can read it. I will leave a link in the description of this video. In Zokyo's and Watchpac's report, there was no mention of reentrancy protection. This was likely because all pending market registrations on Penpie were restricted to the contract owner, the multi-sig of the Penpie team. At that time, mitigation concerns about reentrancy attacks from a malicious SY contract, it was out of scope, right? So because this function was admin only, that can be accessible only from the multi-sig, then it was out of scope. So they didn't report it, they didn't check it for reentrancy attacks for this kind of reason. And then what happened is that around 1 year later, in May 2024, the Penpie team introduced permissionless pull registration. That's bad, right? Because these functions were not audited, right? Watchpag and Zokyo didn't take a very good look at these functions, because if they would see that they are vulnerable to reentrancy attacks. It was not included in the scope. So that's the core issue. They updated the code, they removed the access control, anyone could register new pools, and it wasn't protected by reentrancy guard. It did not follow the checks effects interactions pattern, and that's how it got hacked. So it brings us to the next subject, where relying on audit is definitely not enough, even if you hire top-notch firms. And now we want to ask the following questions. What could help? Okay, we could get another audit, we could include it in the scope. Every update we need to audit again and get new auditors, but maybe there could be another solution that would help in this situation to prevent this hack and maybe detect this vulnerability. And I can tell you what they didn't have in their code base, and this thing is called mutation testing. Now, you might have heard about unit testing and invariant testing and fuzz testing and formal verification if you're in the space for a while, but you probably didn't hear about mutation testing. And in today's video, we're going to show you everything about mutation testing, how they work, and even show you a demo of how you can integrate them into your smart contracts and your code base. So mutation testing basically stands for mutating your code, changing the code, and seeing if your test coverage is able to catch the bugs that were introduced by the new mutations. Now, this sounds a bit weird because it's a new concept that you might not be familiar with, but you can think about it that way. You have a smart contract that has certain lines of code that execute certain line of logic. Then you have your tests that are testing this smart contract. Now, if you change the code of the contract and you mutate it or change the logic or introduce new functionality or remove some kind of existing functionality, and your test coverage, your tests do not break, they are not killed, they're still working and they pass, this could be a reason for a problem in your code base. Because if your test couldn't catch the changes of the code, the changes of the logic, then it might imply that you have an issue in your code base. You have an issue in your smart contract that can be exploited. So in mutation tests, if they survive, if the mutation that we introduced to the code base, to the smart contract survived, then it's a bad sign that you want to check your test coverage and check your smart contract and why the mutation survived. And here is a diagram that explains better what are mutation tests and how they work. So you have your smart contract, then you apply mutation on your smart contract and you have a mutated contract. So it's your original smart contract with a small change, a mutation. Then you run all your test coverage on the mutated contract. If the tests do not pass, this is a good idea. If the tests fail, it's good, right? You can see a green arrow. So if they don't pass, it's good because it means that it catches the mutation, it catches the change to the code, to the contract, and it means that your contract is secure. But if the test passed, that's a bad sign. It means that they're incomplete. You change the logic, you change the contract, but your tests are still passing, which means that there is some kind of state changes or functionalities that are not tested in your contract. And it means that you need to write more tests to cover them and make sure that the next time that it's mutated, your test will fail. Now you do it over and over again with different mutation and try to find bugs that are usually hidden, that WatchBug and Zokyo probably missed because it was in a function that is protected by only owner. They didn't take a look at it. But if it would be mutated and they could see that if they change this function, something still passes and something still goes through and we're able to exploit the contract. And here is a code example. So on the left side, you can see a simple deposit function, whatever, to a Solidity smart contract. And now we want to ask the question, are tests going to break? So we have the deposit function, and then the mutation that we introduce is just to remove this require statement that message value is greater than 0. And you can see here on the right side that we remove this line of code. And if we remove this line of code, we want to answer the question if our tests gonna fail. If they're gonna fail, it means that this mutation broke the test and it's good. If the tests are not failing, it means that it's bad because we mutated the code and our test did not catch it. And this was just one example. This is the tip of the iceberg. Bear in mind that mutations could be all kinds of changes. For example, you can change the condition inside a require statement or in a if statement, or maybe the values themselves. There are plenty of ways to do mutation testing. The concept is that you change one small detail or one small element and then try to see whether the tests break or not. And now you might ask, all right, so how do I change the code? What, do I go line by line, change every time something else and do it manually and then run the test again? How do I know what to change? It's going to be a huge headache and take a lot of time. There should be a tool that does it automatically for me, that every time I introduce a new mutation to the code, run the code base and give me a report of how it works. And that's exactly what we're going to see in a moment. So you're not going to manually change the contract line by line. Don't worry, that's not what we are here for. Lucky us, we're going to use Olympix, which is an AI mutation testing tool. I already recorded another video about the scanner of Olympix that integrates to your VS Code and find vulnerabilities automatically and report it to you, whether you are a developer or smart contract auditor. And this is another tool by Olympix team that introduces mutation testing to your smart contract and allows you to find hidden vulnerabilities that you probably couldn't find without this tool. And what Olympix does is automatically mutate your contract and introduce new mutations, change the code, and run your tests. It checks if the tests are breaking or not, and then send a full detailed report to your email with a complete summary of which mutations survived and which mutations were killed. And the result is you finding hidden bugs that you couldn't find before thanks to this mutation testing tool. And this is how the email looks like. We're going to see it live in action in a second. This is the perfect tool for Web3 smart contract developers that want to make sure that their code base is secure and their smart contract is secure, and they have enough testing that cover all the different state changes, all the logic operations that happen in the smart contract, and also for security researchers. When you audit a new code base, whether it's a audit competition or just an audit for a client, it's a great tool to have in the tool set that can help you find those hidden vulnerabilities that you couldn't find otherwise. You know what? Enough talking. Let's see the tool in action, and now it's demo time. To demonstrate the Olympix mutation testing tool, we created a repo with a simplified version of the Penpie attack. So we have here a saving account, and we have deposit and withdraw function. Now, it's not just a deposit, simple deposit and withdraw function. It's like a bank. And if you deposit more than 100 ETH into the bank, you're a loyal customer, and then you have loyalty bonus, right? This loyalty bonus is you get another extra 1 Ether. And here in the withdraw function, if your balance is greater than this amount, the loyalty bonus is applied, and then a state variable is being updated that you withdrawn your bonus. So it's a very simple, straightforward smart contract, and obviously it's vulnerable to reentrancy attack because, as you can see over here, the send fund function is an external call that sends ETH to the recipient, which we control. So it could be a smart contract that re-enters the withdraw function and withdraw again and again the loyalty bonus because this state variable has withdrawn bonus, was not updated yet. We don't follow the checks effects interactions. We have here an external call, and then here we update the state later. This just simulates the Penpie attack where the reentrancy wasn't that obvious. It was a certain if statement or certain function that only if certain state is happening, only then the function or the contract is vulnerable to reentrancy attack. So if it's lower than 100 ETH, then it's not vulnerable, right? Because we don't enter to this block, right? And then we don't change the state. But if it's higher than 100 ETH, then it's vulnerable. And here we have another contract that exploits these reentrancy attacks. And we have tests. So this is the reentrancy attack test to demonstrate the reentrancy attack. And these are tests to test the smart contract. So now we can just write forge test to see that all tests pass. We can see that the contracts compile and the tests pass, both the unit test and also the reentrancy attack works. So we're able to drain the contract. Pretty much all the functions are being tested here. Test deposit, test loyalty bonus amount, multiple bonus withdrawals, multiple users bonus application, total deposit update on bonus, test withdrawal. But the test coverage here is not enough. We are not able to find the reentrancy attack on the test, right? We couldn't catch the reentrancy bug in the current test coverage. All these functions did not detect the reentrancy vulnerability. So now you're a developer and you want to find those hidden bugs that are not being covered in your test cases, and you want to cover them on the saving accounts.sol smart contract. So in order to run mutation testing on the saving account.sol contract to find those hidden bugs, all you have to do is just run the Olympix tool together with the generate mutation test flag, -p, give it the path of the saving account, and it will start working for you in the background. As you can see, starting connection established, scanning files, starting mutation test generation. And now you will receive an email to your email address that is configured with Olympix with all the report of all the mutations that were introduced to the code, whether they survived or not. And in my email box, now you can see I received a new email with a summary. So the saving account.sol file was tested, 11 mutations were introduced to the contract, 2 survived and 9 killed. So the score is 82%. And if we want a detail, we have a CSV file over here, which we can open with Google Sheets. And here you have a detailed table of all the mutations that were introduced to the contract. And we have here 11 mutations, and these are the 2 mutations that were not killed, which means that your test file did not catch these 2 mutations. You see, these ones are false, which means that it's bad. Here we have all the mutations that were killed by your test. It broke some of the test. For example, when on line 16, message value was changed from message value greater than 0 to message value lower than 0. The tests were killed. Test reentrancy attacks, test deposit, test loyalty bonus. A lot of tests were killed. All these mutations that were killed, but here we have 2 mutations that sneaked through the test coverage and weren't killed. For instance, when the loyalty bonus threshold is being changed from 100 to 101 Ether, we don't have a test that checks the amount of the threshold, which is suspicious. And also, when you change here has withdrawn bonus from false to true, also your tests are still passing, which means that it might be problematic in this function, in this line 34. So if we go now to line 34, we see that this is exactly the issue, because we re-enter the function and we're able to withdraw more and more loyalty bonus, even though we already withdrawn it, because this has withdrawn bonus state variable was not updated. So this is how we can potentially find hidden bugs, like in this example, when we have a code that is inside an if statement or out of scope or a bit more complex function. This mutation test can help us find those issues, and it's a great tool to add to your arsenal if you're a smart contract developer or a security researcher. Now, if you want to try out this tool for free, we have a special link in the description below that will give you a 1 month free trial. It's a Google form that you can submit your information, and then the Olympix team will come back to you to try out this amazing beta tool. And you have a 1 month free trial, and then also a 15% discount if you decide to continue to use it after this 1 month. So if you want to get this special promotion, click the link in the description below, fill in your details, and the Olympix team will reach out to you. If you have any questions, feel free to ask them in the comments section below. And if you enjoyed this video, make sure to subscribe to the channel and smash that like button. Thank you so much, and I will see you in the next tutorial. Bye bye.